Jai Hind everyone. I am Nikita Jaiswal from Ajay Kumar Garg Engineering College, and this lecture on force on submerged body, this is continuation of the previous lecture we have just done at. So we now we have introduced to the concept of submerged bodies and how drag and lift forces actually act on particular body, and what is streamlined body, what is streamlines, what is what is the rate of flow, what is the velocity with which any flowing fluid is acting over any object, any submerged object, and how that flowing fluid actually exert pressure, exert drag force, exert lift force, and what is the resultant force, how that resultant force are acting with horizontal, how we can calculate it. So all the concepts we have already studied, like drag and lift. Okay, so how that drag and lift are actually acting on particular body. So we have yet know how we can calculate it. We have seen the formulas of FD, FL, how we can calculate drag force and lift force. We have gone through all these concepts. Okay, so we are solving some problems. Okay, so in the previous class we have done 2 numericals. This is the third one, and now we are continuing with this numerical in this particular lecture. Okay, so here this is problem number 14.3. I have taken this numerical from your book R.K. Bansal. Okay, so the problem states that find the difference in drag force exerted on a flat plate of size 2/2 when the plate is moving at a speed of 4 meter per second normal to its plane, and the first in water, the second is air of density 1.2 kg per meter cube, and coefficient of drag is actually given as 1.15. Okay, now you just recall what is given here. You can see the drag force exerted on a flat plate. The flat plate is given and the size is given 2/2, that is 4 meters square. The plate is moving at a speed of 4 meter per second normal to its plane. Okay, now the plate is moving. Okay, plate is moving in what media? The first is water, second is air. Okay, velocity of plate here it is given as 4 meter per second. The first media is water, so we are going to solve it for the first media. So difference in the drag force exerted. Okay, what is the difference in the drag force? That means the first we are going to calculate the drag force in water, then second we are going to calculate the drag force in air. Okay, the formula we know very well. The formula now, FD equal to half CD area multiplied by density multiplied by free stream velocity square. Okay, where the first one is our first point is water. Okay, our first medium is water. So the density of water is simply 1000. That should be 1000 kg per meter cube. Okay, now solve it. You will get as FD equal to 1.15. 1.15 CD is given as 1.15. Okay, area will be 4 and density will be 1000, and velocity is given as 4. So 4 square by 2. So ultimately we will get FD as 36800 Newton. Okay, so this was drag force when the plate is moving in water. Okay, now the second point, our second question was drag force when the plate is moving in air. Okay, so when the air is the media, we'll take the density of air. Okay, that is given as 1.24 kg per meter cube. So just apply formula CDA rho U square by 2, where U is given as U of 4, CD is given as 1.15, area is 4. Just one parameter is changing here, that is rho. That is rho for air is 1.24. So now the drag force in air you will getting as 45.6 Newton. See, in the previous lecture, what I have told you, that whenever the media is changing, okay, whenever the media is changing, obviously the drag force will be different for the same case, because the drag force depends upon the density of media. Here you can see from this example also, when the media was air, the drag force was 45.6 Newton. But when the media was water, okay, the drag force was 36800, far more than this value. So the effect of media comes under consideration when we are calculating drag force on a particular body. The main question was, find the difference in drag force exerted. Okay, so what will be the difference in drag force? So simply you need to just difference it. So 36800 minus 45.6, so that will come as 36754.4 Newton as your answer for this particular question. So now the next question is having problem 14.4. A truck is having a projected area. Now the case is of a moving vehicle. The truck is having a projected area of 6.5 square meters traveling at 70 km per hour. Has a total resistance of 2000 Newton. Okay. Now in this question, what we are talking about, a traveling vehicle with a projected area is given as 6.5 square meters or meter square, and the speed is also given. Has a total resistance of 2000 Newton. What does that mean? We'll discuss it later. Of this, 20% is due to rolling friction and 10% is due to surface friction. Okay. Now the concept of different kind of friction is now coming. Yes, okay. The rest is due to form drag. Okay. So three type of frictions are actually considering in this particular question. Calculate the coefficient of form drag. Okay. And take density of air as 1.25 kg per meter cube. Okay. So obviously this is a question of moving vehicle. Here you can see the area was given as 6.5 meters square. So simply this was given. Speed of truck was given 70 km per hour. You can convert it in meter per second. So this will come as 19.44 meter per second. Total resistance was given. Okay. Ft was given as 2000 Newton. Now what other things are given was a rolling friction resistance is 20% of total resistance. So what we will do, just take 20% of 2000, what you will get? FCS 400 Newton. Okay. Second was surface friction resistance, that was 10% of total resistance. Okay, so 10% of 2000 will be what? 200 Newton. Okay. So form drag will be what? Simply just a difference of total resistance minus FC minus Fs. Okay. So left drag is now 1400 Newton. So this form drag is actually we are using in our formula of FD. Okay. So FD, what the formula for FD? CD A rho U square by 2. Okay. What we have calculated, what is FD now? 1400. Okay. The question was asking for calculate the coefficient of form drag. Okay. The question was asking for just calculate the value of coefficient of drag or CD. Okay. So when you apply this formula here, you know the other values, just CD you need to calculate CD. Okay. FD is now what? 1400. CD you have to calculate. Area was given as projected area of a truck 6.5. Now rho is what? You have taken the media of air, that is 1.25. So just take 1.25, and here U is 19.44 you have calculated just before. So here you can take CD, equation for CD, and CD will come as your 0.912. Okay, so this is just a coefficient, so this is unitless. Okay. So this was how you can calculate for any moving vehicle. Okay, you can calculate forces, you can calculate coefficient of drag. Okay, next question is, a circular disc which is 3 meter in diameter is held normal to a 26.4 meter per second wind of density. Here the density is also given with 0.00212 gram per centimeter cube. What is the force required to hold it at rest? Assume coefficient of drag of disc is 1.11. Okay, the diameter is given. You can calculate the area of a particular circular disc. Obviously, just apply formula of air pi by 4 d square. Okay, velocity of wind is also given and density of wind is also given here. Okay, so just a simple question. Here here the velocity of free stream velocity is given as 26.4 meter per second. Okay, the density is given in gram per centimeter cube. Just convert in kg per meter cube. Okay, what you will get? The media of wind. Okay, so simply that will come as, here you can see 1.2 kg per meter cube. Coefficient of drag is also given, that is 1.1. so just you need to calculate the force required to hold the disc at rest. It is equal to the drag exerted by force by the wind on that particular disc. Okay, so simply just you need to calculate the drag force. Okay, so drag force will be what? CD is given as 1.1. Okay, area you can calculate by applying this formula. Okay, the area was calculated as 7.0685 meter square. Okay, rho is simply what? 1. Okay, rho, where is rho? Okay, here 1.2. Okay, so this is rho, and velocity will be given as 26.4 meter per second. Just apply in this particular formula and you will get 3251.4 Newton as answer for this particular question. Okay, next question. All these questions are basically of drag force, where you can apply the drag force formula. Okay, the situations are different. So here is a question when man weighing 981 Newton descends to the ground from an aeroplane with the help of a parachute against the resistance of air. The shape of the parachute is hemispherical of 2 meter diameter. Okay, so here the shape of parachute is given. Okay, this is hemispherical and 2 meter in diameter. Okay, find the velocity of the parachute with which it comes down. Assume CD as 0.5 and rho of air is given. Obviously, density is given, and in gram per centimeter cube you need to convert in kg per meter cube. And here also one particular term is given as kinematic viscosity, 0.015 strokes. Okay. Now this is a case when a particular man is coming down with the help of a parachute. Okay, and then we need to calculate velocity of the parachute. Okay, so in this particular question they are asking for u infinity or u. Okay, so the formula was simple for FD, CD multiplied by area multiplied by rho u square by 2. Okay, so weight of man was given as 981 Newton. Okay, and so if see just for an example, like say this is a parachute and particular men are coming down with this weight. See, the weight of that men is 981 Newton. Okay, what we are saying, the weight of that particular man is 981 Newton. So this weight will be obviously whatever will be the weight, and that particular weight will be equal to the drag force applied by wind. So you can take W equal to FD, that will be equal to your obviously yours 981 Newton. Okay, that parachute with man is actually having a settling velocity or terminal velocity. The terminal velocity concept is different. We are going to study it further. So here diameter of parachute is also given. This diameter, okay, the diameter of parachute is given as 2 meter. If diameter is given, now the projected area means what? Whatever FD is acting will be acting on a projected area, not on this area. Projected area. So what will be the projected area? Diameter is given. You can apply the formula pi by 4 d square. So your projected area will be pi meter square. Coefficient of drag is given as 0.5 here. Okay. Density of air, just calculate in kg per meter cube. That will be your 1.25 kg per meter cube. Let us suppose the velocity of parachute with the velocity with which that particular man is going down. Let us suppose this is u or u infinity, whatever you want to take. Okay. So this is u infinity. Now just apply in that particular formula FD equal to CD, area rho u square by 2. Here you will get as FD equal to W or equal to 981. Okay. CD is given as 0.5, area you have calculated as pi, rho is 1.25. All the other things are given, just you need to calculate this parameter. Okay. So the velocity of parachute with which it comes down will be your 31.61 meter per second. This is the same question, just with a few parametric difference. Okay. The diameter, again, this is a question of parachute. You can solve it. You can solve it easily. Okay, just you need to apply the same formula. Okay, just take a look and solve it. This is another question. This question is containing actually the weight of ball of diameter 80 mm. So we can solve it. The question is, calculate the weight of a ball of diameter 80 mm, which is just supported in a vertical air stream, okay, which is flowing at a velocity of 7 meter per second. Here your u or u infinity is given as 7 meter per second. The density of air is 1.25 kg per meter cube, and kinematic viscosity of air is given as again 1.5 Stokes. Okay. So diameter is given as obviously 80 mm. So this will be equal to a 0.08 meter. Okay. Velocity is given as 7, rho is given, and here kinematic viscosity is also given. So the kinematic, here the purpose of giving the kinematic viscosity is actually to calculate coefficient of drag. Okay. When the Reynolds number is actually in some particular range. Okay. So you can follow what will be the value of your coefficient of drag. Okay. So here when you calculated Reynolds number, the formula for Reynolds number is velocity multiplied by diameter divided by kinematic viscosity. Okay, the kinematic viscosity is given as 1.5 multiplied by 10 to the power minus 4 meters square per second. So just calculate it. Reynolds number is coming as 3730. This value lies in between 1000 and 100,000. For which particular bandwidth, or you can say the range, the CD is 0.5. Okay. Then now just going further, when the ball is actually supported in a vertical air stream, okay, the weight of ball will be equal to the drag force. Obviously here in this figure you can see this is the ball, this was the ball. Okay, the weight was acting downward, and this is this lines is actually what, see, you can see the lines are coming from this direction, then going like this in this direction. So these are actually flow lines, or you can say streamlines. How these streamlines are acting over this particular streamlined ball. Okay, this is showing in this particular figure. The diameter of the ball is also shown, 0.08 meter, and this is what, this arrow is what is actually drag. Drag is what? Simply whatever the air is applying a force over that particular ball is drag. Okay. So next step is your drag force. How you are going to calculate drag force? As CD area rho u square by 2. Okay. The projected area of ball. Okay, you need to understand this concept of projected area. Okay, the diameter of ball is given. Okay, so in that particular diameter, what is the projected area? Simply a circle. Okay, so projected area of ball will be what? Pi by 4, 80 mm square, or you can say 0.08 square. So this will be your projected area, 0.005026 meters square. Now the drag force will be what? Simple. 0.5 multiplied by area rho u square by 2. So you will get as drag force as 0.07696 Newton, or you can say it as simply weight of ball. You will get as 0.07696. See, this was a case of ball. Okay, indirectly they were asking for actually drag force. They have asked for calculate the weight of the ball. Okay, and the situation was all the parameters were revolving about drag force, revolving around the drag force. So just all the given, sometimes what actually happens with students that they get confused. What kind of forces are involved, what kind of formula we are going to apply. So just see what is given in that particular formula. You will just connect what topic, in what chapter you have to go, what theoretical analysis we have to follow. So when there is given parameters that revolves around density, viscosity, and air pressure, air velocity. Okay, so just you can click, and obviously this is very simple. Numerical in which the weight of the ball, they are asking for weight of the ball. Obviously, when the particular ball is streamlined, or you can say is supported in the vertical air stream, so obviously this is a case of drag force where your FD will be equal to W. Okay, so here you can calculate by following this particular steps. So this is another question. Okay, now we are moving towards our next topic, streamlined body. Okay, so what is streamlined? Actually, we are going to understand it. Let us suppose this is your first object. Okay, you can see there is a circle around here. And this is your second object. Let us suppose both the objects you have kept it in a particular flowing fluid. Okay, let us suppose that is air. Okay, what I am drawing is actually flow lines or streamlines of flowing fluid. Okay. So this is flowing fluid. This is the direction of flowing fluid I am drawing. Okay, so just see object number 1 and object number 2. Okay, streamlined bodies, that means what? How smoothly, how without more loss of energy, how smoothly can a particular flow lines can pass over a particular body. So just take an example of this two bodies. Here both if you cut this particular object in two classes, okay, you can understand very much this is symmetrical or unsymmetrical body. Okay, still there are some difference when we talk about streamlined bodies. So you can see in the first body the flow lines were moving like this. Okay, but the separation of that particular streamlines from this first object, you can imagine somewhat here. Okay. So after the separation of streamlines from particular body, actually wake zones are created. Okay, we have already discussed what is wake zone in previous lecture. Now go to the second object. Here you can see the wake formation zone is very much at the trailing end of this particular body. Okay, both the objects are actually streamlined. Streamlined means the smooth flow of streamline should be there in particular object. Is that object or the shape or geometry of the object is such that then the particular object you will be said as streamlined body. Okay, here, but in this particular case, in this subject number 1, subject number 2, the wake zone is actually not much farther than this particular zone. Okay. So both the objects are actually streamlined, but when you compare it, you will say that the object number 2 is more streamlined body than object number 1. Okay, so here you can identify what is streamlined body, what is bluff body. What you will call as bluff body. Bluff body is simply what? A particular kind of body where the streamline formations are not regular, not smooth. Okay, so that particular body will see, just draw the random body like this. Okay, so if you put this kind of body in streamlines or particular media, you can say that the stream formations or line formation will be not smooth as like in this object number 1 and object number 2. So you can understand now what is the difference between streamlined body and bluff body. Okay, again, just streamlined body is defined as the body whose surface coincide with the streamlines. Okay, when the body is placed in the flow, coincides with the streamlines. Okay, so that body will be your streamlined body. In that case, the separation of flow will take place only at the trailing edge. Okay, separation of flow, I have told you what is separation point, what is separation of flow. When the particular boundary layer gets destroyed at that particular point, that will be your separation point. And after the separation point, actually wake zone created. Okay. Bluff body, simple word. Bluff body is that body whose surface doesn't coincide with the streamlines when placed in a flow. Okay, that doesn't coincide. A very large wake formation zone is there in the case of bluff body. Obviously, whatever the wake zone, okay, how large the wake zone, that means how the bluff body is acting. The way the wake zone is there, that means the separation of boundary layer is there. Okay, the drag force due to pressure will be very large as compared to the drag due to friction on the body. Okay, so this is how we can conclude streamlined body and bluff body. Now the next topic is drag on a sphere. Okay, what is sphere, you know very well. Now when we talk about drag on sphere, so there are some particular parameters we need to consider. So consider the flow in a real fluid past a sphere. Let us suppose there is a sphere. Okay, a sphere of diameter d. Let us suppose the diameter of d, and velocity of flow fluid passed over a sphere. Let us suppose that is capital U. Okay, the mass density of particular fluid is rho, and viscosity of fluid is also given as mu. Okay, now if the Reynolds number of flow is very small, how you can calculate Reynolds number of particular flow? Okay, rho Vd by mu, or you can say it as Vd by kinematic viscosity. Okay, so here you can calculate Reynolds number. Here is also written as rho u d by mu. U is actually velocity, velocity of what? Of this streamlines. Okay. If the Reynolds number of flow is very small, or you can say less than 0.2, the viscous forces are much more important than the inertial forces. Okay, viscous forces are more important. Inertial forces are not, we are assuming it as negligible. So up to this condition, what condition? When Reynolds number is less than 0.2, the Stokes was G.G. Stokes developed a mathematical equation to solve how the drag force will be acting over that particular sphere. Okay, but he actually neglected inertia forces. Okay, because he neglected inertia forces in the case against when we are considering only viscous forces. Okay, so according to his solution, the total drag was, simply the formula is written here. Okay, FD is simply 3 pi mu d and capital U. Okay, so this is the drag formula he concluded on the base of his experiments he have conducted. Okay, on the basis of that, he also told what is skin friction drag and what will be your pressure drag. So skin friction drag is a 2/3 of this particular FD, and pressure drag will be 1/3 of this particular FD. Okay, whenever someone asks what will be the total drag force, so you can calculate by applying this formula, and again the further just take 2/3 of this FD, that will be your skin friction drag, and 1/3 will be your pressure drag. Now the expression of CD for a sphere when Reynolds number is less than 0.2. Okay, when it is less than 0.2, then the formula you need to remember is this one. You can calculate by applying this particular formula. Okay, so the value of CD will be equal to a 24 by RE. Okay, so expression for CD for a sphere when Reynolds number is less than 0.2. Now you can apply the equation for CD as 24 by RE. But when the second case arises, when RE ranges between 0.2 and 0.5, what will be the formula for CD? He has taken as 24 by RE in bracket 1 plus 3 by 16 RE. Okay. Now the third case arises when RE is in between 0.2 and 5. Okay. Now the formula is again CD equal to 24 by RE 1 plus 3 by 16 RE. So there are other 5 cases here when the ranges of Reynolds number of 5 to 1000, then he have taken CD as 0.4. When the range was 1000 to 100,000, the CD was taken as 0.5. We have just calculated, we have just solved a numerical in previous slide where we have taken CD as 0.5 because the Reynolds number range was in between this. Okay. Next topic, next case, CD for RE when RE or Reynolds number is more than 10.5, then you can take CD approximately equal to 0.2. So this is for all for today's lecture. Here we have concluded, we have calculated different problems. Okay, here we can calculate CD, we can now we can calculate CD and how the different situations can be acted upon a body, how we can calculate coefficient of drag and force due to drag. Okay, and also we have seen what will be the drag on a sphere when the particular Reynolds number is less than 0.2, how Stokes have calculated force of drag, okay, when Reynolds number is less than 0.2. So this is all for today's lecture. Thank you everyone. Jai Hind.